Yeah, so okay, I just studied these differential equations with some flow perturbed by some dynamic given up there. And what happened is that the dynamic of the main dynamical systems has some kind of fast motion that we will just accelerate, and we look at what will be the behavior, the asymptotic behavior of the slow motion associated to that. So the slow motion, which is given by the solution of the differential equations, and we also expect some kind of rate of convergence of that slow motion. Okay, these are the two main questions. And as an example of dynamical systems, so the one m phi mu we got before, well, I will mainly use dynamical system derived from the Sinai billiard, so which is the one exposed there. So you just take the torus with where you this square where you just identify the boundaries. And on that torus, you just glue a family of obstacles. Here you have two obstacles, O1 and O2. And the behavior in that scenario billiard is basically the behavior that of a particle that goes straight and just bounce against the obstacles, following some kind of reflections. So just conservative movement with unit speed. Okay. This kind of systems actually have been studied for themselves. There are some kind of probabilistic preserving dynamical systems, and we have we know for quite some time some result about what is the behavior of that slow motion xt epsilon that we had there. Well. So it converges to some kind of average process, which is given by purely deterministic differential equations, and we even get some kind of limit theorem for the rate of the error term between this average solution and the slow motion, which is just written there as some kind of stochastic differential equations. I will just keep this setting for now. So I just recall that. I'm not sure if I. Sorry. Maybe I will just use the other blackboard. So yeah, we have our slow motion dx t epsilon over dt, which satisfies some perturbed differential equation there. And yeah, we have these solutions that converge to some solution omega. And with some kind, this kind of error term there. But this is for the continuous dynamic, so a continuous a dynamical system with a flow. But we can also study the same thing on the collision process associated to the scenario billiard. So this collision process is the one when you take some kind of Poincare section as the boundary of your obstacles. And the dynamic is just give you the time, the state of your particle after the next collision on the on each obstacles. And for this system, the two are related as some kind of special flow. You can define some kind of room growth function over the collision dynamic that provides you a system which is similar to the one we saw, which was the Sinai billiard. And just for the sake of the talk there, we also keep this proof function to be bounded, which is what we call the finite horizon hypothesis. So for the collision process, we can also define some kind of perturbed differential equations that looks like this. So we, instead of having to study a flow, we study the iterations of the collision dynamic. And we have, okay, and when we want, when we are looking at the special flow over this collision dynamic, which is, okay, the Sinai billiard, it's what we are actually doing is, okay, we can state some results on that collision dynamic and then lift it to the flow dynamic. So this is the result with, okay, for the collision dynamic. So you have this kind of average solution, which is totally deterministic, and you can recognize there okay, the SDE, the stochastic differential equations, but with another rescaling through the time that is compared to the one before, and that's just depending on the roof function you had, and the mean, the average of your roof function. Okay, just a few words, but this is not the main theme in the topic, but a few words about the way we prove that theorem is, okay, an interesting decomposition of the our vector field. So we split our vector field in two components. One which is, let's say, stationary, which is just the mean of our vector field over all the possibilities in our billiard, in your dynamical system. And we have some kind of centered part there, which is, okay, everything else once you remove that that mean flow. Okay, and each of the terms that appears in that decomposition actually contributes to the stochastic differential equation we got there. Because the first term, this F tilde, which is the centered one, just brings you some kind of Birkhoff sum, and so the one of this kind, and through some, and in the nice hypothesis we got from the billiard, this Birkhoff sum just behaves like some kind of Brownian motion, and we thus get this limit there. That just is, okay, a consequence of the variations of that Birkhoff sum. And the next term, so the stationary part actually brings you some kind of, okay, just appears in the variational formulation you got from, okay, when you just perturb the initial value within your initial differential equation. So, okay, I just remember that the limit process you got there, which is this d omega t dt, just satisfies some, okay, totally deterministic differential equations, which is like this f bar of omega t. So when you derived it and you look at, okay, the derivation of the initial value, you just get this term there, which is the one appearing there. Okay, this explains a bit, just roughly, how you just got the theorem before. But the main point is, okay, to get that, we had to do this nice decomposition. We have f, so the vector field, which is integrable on our finite dynamic, or probability preserving dynamic, and we decompose it into a stationary part and a centered part. Okay, but the thing is we want to study some, okay, the same kind of system, so the same kind of differential equations, but in the particular case of well, some measure preserving systems. So okay, we can no longer keep these two main features, which is having either the flow, the vector field integrable, and this decomposition into a centered part and a stationary part. Why? Because this stationary part is no longer something you can integrate with a finite value. So we just look at both systems in what follows. Okay, and I also just say a word about the kind of system we look at. Actually, so we had the example of the billiard systems, which was, okay, a finite probability preserving systems. But now we look at obstacles no longer on a torus, as before, but on a cylinder, which gives you this, okay, so you just identify the two boundaries there, and you still keep the same dynamic, so you go from obstacles to obstacles through some kind of collision time there. And these obstacles are just put periodically through one direction, so the main direction of your cylinder, which gives you that instead of having two obstacles, O2, O1, you have a family of periodic motifs with two patterns, which are O1 and O2. So, and we just index them, making some kind of cells through the dynamical systems. So you can represent this so this Z-periodic collision process as some kind of Z extension, in the sense that the dynamic is entirely provided by, okay, your Sinai billiard, let's say, your collision process on the Sinai billiard is M bar, T bar, mu bar, and some kind of step function that just tells you in which cell what will be the index there of the next obstacle you will encounter for the dynamic. Okay, and so this is an example of, okay, this gives you this nice dynamic. So it's a skew product. And if you iterate, you can see that your step function just iterate has a Birkhoff sum. Okay, so studying the collision process, which will be our main dynamical systems that perturb our differential equations for the Z-periodic Lorentz gas, amounts to know precisely the dynamic in the Sinai billiard I presented before. Okay, we can state a few things then from the dynamic, so the skew product, but taking into account that or basis or basis for our system is the Sinai billiard. And one main point is that the theorem from Vinimovich and Sinai that just states that these Birkhoff sums satisfy some kind of functional central limit theorem. So it converges to some kind of Brownian motion. And okay, for the sake of the talk, I just precise there that to Brownian motion we can actually associate what we call a local time, which is okay. This quantity there, I just write it to keep it. So it's just the density of how many times your Brownian motion passed through some small area. Okay, and in that case, if we suppose from now that f is just something integrable, we can even take something a bit stronger. We take it with compact support, so it's an integrable function. Okay, the vector field is seen as integrable in second coordinate, in the coordinate that depends on the dynamic there, and we assume that okay, the strong hypothesis that it actually takes its values in the central cell. So it varies. It is non-zero only when you hit the obstacles which are indexed by 0. Well, in that case, we don't have an averaging of the slow motion there, but directly a limit. And actually, the process gets slowed and just converge to, and when the dynamic accelerates, it just stays close to the initial value we got. It started. The slow motion started. Okay, and we have some kind of local limit theorem that makes the intervention of this local time. Okay, and just a precision. Okay, we are talking about dynamical systems which are measure invariant. So we look at some kind of this is a limit in distribution. It's a limit in distribution for any probability measure absolutely continuous to the one embedding the system, or Lorentz guys in our case. Okay, so just a few words about the proof of that theorem. Well, it essentially lays on the fact that our slow motion, so our xt epsilon there, only moves when our vector field just reach the dynamic hits the cell 0, so this one. So we just basically count how many times we reach that cell. We are just looking at that event, which is basically a rare event that, since this we are looking at this for the Z-periodic Lorentz gas, and for Birkhoff sum, we saw it in the Dynamical theorem, behaves a bit like, you can think of it as a random walk, so in a one-dimension space. It is recurrent, but it's it goes to infinity, and this the slow motion is just comparable to this motion there, which get just slowed by the ways let's say the discrete local time behave. And since you have this this local time, it's through the Bunimovich-Sinai, but you actually need a bit more than the Bunimovich-Sinai theorem to state the convergence of that discrete local time. You can use some kind of decorrelation properties that are really useful on a billiard, Sinai billiard. To get the behavior of that process. And so you can notice that your slow motion gets really slowed. Actually, the typical time for this is of epsilon, square root of epsilon, which means that you basically just stays close to the initial value. And so this is just what happened. You just see that process as looking at a Lipschitz process with a first derivative. You have your first derivative there, and this is your typical time you spent moving. The proof of that is done by some kind of induction on the zero cell. That was for the collision process, but we can then just state it for the Lorentz gas, the Z-periodic Lorentz gas, which is again the special flow over that collision process. We just see there, and to describe it, so you just move through the whole space and not just the boundary of your obstacle, your Poincare section. And the generalization of it is just okay, just a few results from Y.Kifer in 1995, where you approximate your system, your slow motion, by okay, there are few typos, by some process satisfying some differential equations where you average your you kept your stationary part, but you had some kind of typical heating time, which is given by your rho function there. Okay, and yeah, and through this lemma that states that okay, you keep some control between the difference of these two solutions of the differential equations, and from that control you also can control the typical number of crossing of the Poincare section, which is this quantity nt over epsilon, which I should write maybe. So this nt is just the supremum of, let's say, omega for k, such that the sum for n, that the sum of the iterated hinting time is below, okay, this time t. This is basically a Birkhoff sum, and it's it converges to sometimes rescaled by the typical average time for your rho function, so your heating time of the Poincare section. Okay, and the rescaling that appears in the theorem back there, just comes from that, okay, that type of convergence. Okay, this was for the, okay, what happened in the particular case where we have a vector field f integrable. Now we look at the next point, which is when f is just can be separated between the stationary part fr and the centered part f tilde. Well, in that case, you kind of recover okay, an averaging theorem with this same limit omega s ws, which was given there. So it really looks like it has some familiar setting with the dynamical systems, the probabilistic probability preserving dynamical systems, except that the limit which appears there has some local time in it appearing, and maybe it gets a bit more easier to see when looking at it in one dimension. Because in that case, the limit process you got there, this VT, is just Brownian motion against, okay, some kind of variance given there, which is this A of omega s. Okay, which is okay, and so the main difference with the theorem we had before, and I should have written it, is this local time appearing there, and we have also additional hypothesis on the behavior of f of our main vector field when we go away from the let's say the central cells. So we have some kind of vector field that when our dynamic moves away from the central cells, the obstacles indexed by 0, 1, etc., then the vector field just vanishes. You have some kind of figure of this type. Okay, this is your main cells. it goes to plus infinity and minus infinity. And your vector field over this just is kind of concentrated in the center of your systems. Okay, these are the main hypotheses and kind of additional ones. And these are also the one that explains this the separation of that local time. Okay, to prove this, this behavior of the slow motion, we can focus on this. We can for now just state this this perturbed ergodic Birkhoff sum, which is just given there with some kind of rescaling in time. And the error term, this ET epsilon, which is kind of derived from there, which is the difference between our slow motion and the average one. Satisfies some kind of variational equations that you obtain through some kind of Taylor expansions, basically. Okay, and this so you have a process that is defined by some kind of variational equations, and for the sake of keeping a process, you also need some tightness, which is provided by nice decoration properties. I will come back to that a bit later. The main thing is that you basically have a function describing your error ET epsilon. Basically, your ET epsilon is some function of this VT epsilon, which is given by, if you assume this similarity to be a strict equality, your function will be just given by some VT epsilon. This is the integral of perturbation, some differential of the perturbed vector. So definitely a deterministic function. So if you prove the convergence of the Birkhoff sum there, since you have a deterministic function, well, your error term is expressed as a deterministic function of your Birkhoff sum, then you will just get the converging of the process just by by a mapping theorem. So we now focus just on this limit there, which is the some kind of limit theorem for the Birkhoff sum. But it's a Birkhoff sum just with a term which is moving, so it's some kind of perturbed Birkhoff sum. And you can see again that the local time appears, and we're gonna just explain that a bit later. How does that term appear? Just to mention that since it's a Birkhoff sum, if that term is constant, we just get back some kind of central limit theorem we get before. So if we have no dependency on the vector field in the first coordinate, we just keep this this limit towards some kind of Brownian process with a perturbation given by this local time, with a local time which is independent of your Brownian motion. Sorry. Okay. Well, so to see the importance this local time, we just focus on some kind of toy model. So assume that instead of having a dynamical systems, which is given by a Z extension, we have this couple Xi and this Birkhoff sum Sn of phi, with xi, which is just randomly picking a state in M bar, so basis for collision process, or Lorentz gas. And Sn phi just acts like an aperiodic random walk. And we also further assume that, okay, since we have some vector fields that kind of concentrate in the main cells of the collision process for the Lorentz gas, we can just take the Thor model of a compact support function. In that case, we can just rewrite or perturb Birkhoff sum, just taking into account the hitting the moment where we hit the zero cell, and we rescale it through. So we just count how many times we hit that the zero cell, and we have this rescaling through the so nt epsilon is this local time, discrete local time, and this epsilon 1/4 factory appears from that local time, because the typical rate of convergence of this local time is in epsilon 1/2. This comes, this is a bit of an extension because we have nice properties over the Birkhoff sum, the Birkhoff sum of Sn phi, so the sum of the iterate of the step function. And so this factor epsilon 1/4, which is the main factor that appears in our averaging, just comes from that convergence there. Whereas the Birkhoff sum there, if you still imagine your IID case, just behaves like a Brownian motion. So you have some kind of result of this process has a limit when you combine everything, and through some mapping theorem for the convergence in law, to some kind of process where you have effectively your local time that just comes out of your discrete local time. But now if we come back to the nice settings, we no longer have IID distributed elements as for dynamics. Instead, we just have the iteration of our dynamic, which satisfies some kind of exponential decorrelation. And the main thing just comes from that exponential decorrelation. So instead of applying some kind of central limit theorem directly, we're gonna use what was told before which is some kind of moment criterion to prove the convergence. So we can state this decorrelation because our dynamical systems or bases, which is this Sinai billiard, just satisfies. For example, you can construct over it some kind of Young towers, which admits some kind of factor, which has kind of expanding factor where you perform Frobenius operator just satisfy some kind of decorrelation this way, which is basically a local limit theorem. And from this, when you go back to the billiard system, you also get the decoration coming from there, and with this n to the power 1 minus 1 over half, minus 1/2, sorry, which is basically the main probability of this being in the cell 0. It appears there. And so you don't use directly the central limit theorem. What you use, in order to use these decorations, you apply some kind of moment criterion, the Kalman criterion typically, that states that if you have the convergence of the moments for your of your process, then you get the total convergence in law for your process. Okay, and the other nice behavior is that when you when you expand this the moment terms appearing there, the decoration just allows you to make most of the term vanishing, and thus you don't have to you just have these terms appearing there, which are the some kind of terms of variance, and brings something that you already encountered in the dynamical systems for the perturbed differential equations when we were crossing the probabilistic dynamical system, which is this one. So, okay, we just deal with the fact that, okay, this term has to be well defined, and it doesn't move much once you look at cells a bit far away from your main concentration point. And this gives you the convergence of the moment. So once you have the convergence of the moment, you have the convergence of your process, but in the sense of finite distributions. But the correlation properties that we get from the billiards just allows us also to look at the second order moment of this of our process, and then to ensure some kind of tightness for our process. Okay, this ensures the convergence, the finite limit, the convergence in distribution, but in the space of continuous functions. So Sadlat functions, but since the limit is continuous, we can state it directly with the infinite norm. And from the convergence of the Birkhoff sums, we deduce the convergence of the whole error terms we have. So the difference between the slow motion and the average one. Okay, so yeah, we stated the theorem for the collision process on the Z-periodic Lorentz gas, but we can also go a bit further and lift it, just as it was lifted in the two other cases we looked at, for the Z-periodic Lorentz gas. So the gas with a dynamic, the system driven by a dynamic given by a flow. And again, we just have, the main difference just lays on some kind of rescaling through the averaged hitting time of the obstacles. Okay, and the limit stays the same, so it's still given by this equation there with some process driven by some the same local time associated to the step function, which comes from the basic collision process we had before. Okay, but so to prove that, we have to go a bit back to the perturbed differential equations for a probabilistic dynamical system. And on those systems, actually the proof can be done in 3 steps. With one is this lemma from Kiefer, where we approximate or slow motion, but the continuous one, by some kind of slow motion, but associated to a collision dynamic. So typically something satisfying some differential equation with that type with a collision dynamic. Then we ensure that we make few the difference between the two main error terms we got from these two processes, when we average them, are actually something that is negligible in comparison to the main scale of the main rate of convergence of this averaging. Okay, and finally we just combine it with the convergence satisfying by the number of times we hit the boundary, so we collide with the obstacles, which is okay, which is given there, and that gives our rescaling usually. Okay, that's the proof when we look at probabilistic dynamical systems. But the thing is, this rescaling is not our rescaling in our case. We have a rescaling in epsilon to the power of 4, and this implies that we may not have the enough hypothesis to get something equivalent to step 2. So in our hypothesis, we just add some additional one, which is, okay, we ask a bit more regularity for vector field or perturbed vector field, and we still keep it centered, but also for the first derivative. And in that case, we can redo the first step, the step 1, and with just a few additional terms that comes from the fact that we are looking at a specific terms with a central part and a stationary part. So you have your heating time there that comes along some stationary part. You have this, and we substitute the step 2 by this kind of something which is close to variational equations, but with some kind of additional error term which is given there. And the main point of asking for an additional derivative for the vector field, is just to make sure that this term will be indeed negligible. So this term is just this one. So the one error you make between the average system and this pseudo-average one. And just by some kind of, from this, you can just make some kind of Taylor expansions, and which makes it appear typically this term there, which is some term rescaling in epsilon, and you have this term there that has just a nice rescaling, because this has rescaling of about epsilon of 1/2, and this has this term, which is a derivative term, is again a Birkhoff sum that we studied before, and that has exactly the same rescaling as our perturbed or slow motion for the perturbed differential equations. So this term will be something that goes that converge faster than in the scale we're looking at, the typical scale, which is epsilon to the 3/4. Okay, and this brings us some kind of convergence. And from that convergence, we deduce the, this proves the main theorem there, and and allows you to lift the result for the perturbed differential equations from the collision process to this Lorentz gas, so the continuous time process. And and actually what we get is that contrary to the previous proof, where we got the perturbed differential equations from some kind of central limit theorem for a perturbed Birkhoff sum. Here we got the limit theorem for the perturbed Birkhoff sum directly from that lifted result on the behavior of the slow motion, so the averaging of the slow motion. So this convergence there, which again marks some kind of rescale in time, just comes from, pretty straightforward. It's just a pretty straightforward corollary. You just state some kind of perturbed differential equations for some continuous dynamic. So we keep our Z-periodic Lorentz gas, and we just state our theorem with some convenient settings that it match the assumptions of the previous theorem for the continuous flow. And this process, AT epsilon, just actually match this VT epsilon term, which is this perturbed Birkhoff sum that I noted it all along. And this proves this brings you the limit as a consequence directly of the main theorem, which was this theorem. So we just basically just keep the limit there from the perturbed differential equations we got there. Okay, and this proof finally some kind of perturbed averaging result for the perturbed Birkhoff sum over the Z-periodic Lorentz gas. And this finished my talk. Thank you.